Good morning, students. We are going to look at the second branch of our unit. In the beginning, remember I told you this unit consists of bioinorganic and organometallic chemistry. We are going to look at organometallic chemistry. Usually this chemistry concerns the compounds containing metal-carbon bond. Therefore, organometallic compounds are compounds in which the carbon atom is bonded directly to the metal atom. This includes carbonyls, carbides, various hydrocarbons, certain chelated complexes, but not complexes of metals with the organic amines, neither carbonates nor metallic salts of organic acids. They also include compounds in which the carbon atom is bonded to a non-metal. Among the non-metals, we have examples of boron, organometallic compounds, silicon, organometallic compound, and phosphorus, organometallic compounds, in which the non-metal is bonded directly to the carbon atom. Classification. They can be classified into three categories. We have the ionic organometallic compounds, and these are formed from highly electropositive metals. Examples are organometallic compound of sodium, organometallic compounds of potassium. These two are largely ionic in character. The ionic organometallic compounds are insoluble in hydrocarbon solvents. They are highly reactive and are among the most powerful bases. Ionic organometallic compounds react explosively with water and burst into a flame when exposed to air, or oxygen. The organometallic compounds of lithium and magnesium are soluble in ether solvent, and the carbon metal bond is highly ionic in character. And because of this ionic nature, the carbon atom that is bonded to lithium and magnesium is a strong base and a powerful nucleophile. Another type of classification is the sigma bonded organometallic compound. These are compounds of metals having a lower electropositivity or non-metallic elements. Examples, we have the silicon organometallic compound, boron organometallic compound, and phosphorus organometallic compounds. And in these compounds, bonding is covalent and their chemistry is organic-like. The last classification is the non-classically bonded compounds. These ones cannot be explained by neither ionic or covalent form of bonding, because in their formation, they form bridges. Examples, we have those alkyls of lithium, beryllium, aluminium, you can name them, and the structure is as below. There are several factors that differentiate organic chemistry from organometallic chemistry. Some of you can think both are similar, but we have several factors which differentiate the two. Mainly, the possibilities of using higher d orbitals in organometallic compounds, and this is particularly true for alkyl tetrasilicon as opposed to the case of carbon. Remember, silicon is having an atomic number of 14, and the electronic configuration is 1s, 2s2, 2p6, 3s2, 3p2, and 3d0. When we look at the carbon, which has hold atomic number 6, the electron configuration is 1s2, 2s2, and 2p2. So the energy gap between the 2 and the third shell for carbon is too high for electrons to occupy the s orbital. Unlike for the silicon, because of the empty 3D subshell, which is part of the valence shell, there is a temporary occupancy of electrons in the d subshell, unlike in the carbon. There is also ease of donation of electrons from the alkyl and the allyl groups to the empty d orbitals in silicon, as opposed to the carbon in organic chemistry. So when we look at the electronegativity difference between the metal and the carbon atom is very large for organometallic compounds, unlike for carbon-carbon, which is having the same electronegativity. Preparation of organometallic compounds. There are mainly 3 methods. We have the substitution method, oxidation method, and reduction method. So substitution method, under this can be of any of the following types. We have the type A reaction. This one involves those compounds containing an acidic hydrogen or a metal less electropositive than the substituent metal. An example of the acidic hydrogen are illustrated in the equations below. So we can be able to prepare the organometallic compound of sodium, potassium using an acidic hydrogen. For the metal, less electropositive than the substituent metal, we can use that method to prepare again the organometallic compound of sodium, magnesium, and zinc. Therefore, the point to note here is that this method is best for preparing alkyls of more reactive metals such as alkali and alkali earth metals, and also zinc. We have the type B reactions. This reaction is illustrated by the following examples, which has been illustrated in the equations. Here we are able to prepare the organometallic compounds of magnesium, of lithium, sodium, zinc, and many others. The type C reaction has got the following reactions. We have metallation. This term is usually used restricted, or this term is usually restricted to metal hydrogen exchange reaction, where the metal exchanges for hydrogen as illustrated in the 3 equations. We have the organometallic compound of sodium in different methods, in different reactants. Another insertion in substitution method, we have the metal halogen exchange reactions. This is best illustrated by the reaction of halogenated phenol with the N-but lithium, as shown in the equation below. This is the phenol, bromophenol, with the N-but lithium to give us the organometallic compound. Another one is the reaction of organometallic compounds with the metal solids. This is mainly for organometallic compounds which cannot be obtained by direct reaction of a metal with the hydrocarbons or a halocarbon. Usually the starting materials are the Grignardi's reagent. So we can be able to use Grignardi reagent to prepare the organometallic compound of zinc, cadmium, mercury, beryllium, and aluminium, as illustrated in those given equations. Another one is the reaction of bimetallic compound with halide. So many derivatives of group 4B metals and metal carbonyls are synthesized by this method. Examples are illustrated in the given equations. In the first equation, we have two metals giving rise to the organometallic compound of phosphorus. Then in the second one, we have the carbonyl giving rise to the manganese pentacarbonyl. We have the type B reaction. This may be of the following type: displacement of one neutral ligand by another, as illustrated in the two equations. The first equation and the second equation. The point to note here is that the extent of displacement depends upon the metal, type of ligand, and the nature of the solvent used during the preparation. With an example of the nature of the solvent is in the reaction of bromo-manganese pentacarbonyl, reacting it with the cyanide in the boiling tetrahydrofuran as a solvent. All the 5 carbonyl groups in the bromo-manganese pentacarbonyl are displaced. But when we use ethanol, only 2 are displaced. This is illustrated in the given equations. All the 5 pentacarbonyls are replaced, while for using tetrahydrofuran. But using ethanol, only 2 are replaced, and we are remaining with 3 in the organometallic compound. So another method of preparing organometallic compound is additional method. And this method may be of the following types. We have the reactions of metal with the carbonyl and unsaturated hydrocarbon. Examples are given in the equations below. When you react nickel with the carbon monoxide, we get the nickel tetracarbonyl. Iron with the carbon monoxide results into the iron pentacarbonyl. And then for unsaturated, the given equation is as shown below. Oxidation additional reaction. In this additional reaction, the oxidation of the metal is accompanied by an increase in its oxidation state. So an example given here is the cobalt-2. Reacting with the either hydrogen molecule or bromine molecule or others, it can lead to cobalt-3, changing the oxidation number. The last organometallic method for the preparation, the last method for the preparation of organometallic compound is the reduction reaction. So this one can be illustrated by the following reduction reactions. We have the chemical reduction. This is mainly for the preparation of a number of metal carbonyls. Carbon monoxide is the most commonly used reagent or reducing agent, as illustrated in the two equations. We use carbon monoxide in presence of nickel sulfide to give rise to the nickel tetracarbonyl and others. We have also the electrolytic reduction. An example given in this one is shown below in the following equation, where we use tin as the cathode. So next time, we are going to look at the general properties of organometallic compound. Kindly read about them so that we get an interactive discussion.